To the Emerging Scholar Seminar Series. We're really glad to have you. Every other Tuesday, we host a great emerging scholar in the field of material science, machine learning, AI development on both experiment and theory side. So a broad range of topics, and we're really excited by the turnout. Today, we're going to hear from our own Francesco Tavani. He is a Marie Curie postdoctoral fellow who joined us recently at BIDMaP in 2025. Before that, he did his PhD in Rome with the D'Angelo group, and has expertise in XAS and molecular dynamics, so both experiment and theory expertise, and is studying this really hard problem, very important problem, atmospheric water harvesting in meta-organic frameworks, which is, of course, central to the identity of BIDMaP and what we're here to do. So take it away, Francesco, and thanks very much.
Okay, so thank you, Daniel, so much for this really nice introduction. Thank you, BIDMaP, and for this opportunity. I'm very happy to be here. So the title of my talk is Global and Local Structural Insights into MOF Atmospheric Water Harvesting. So okay, so complexity is a matter of perspective. And if we take a big, enormously big crystal, it would be a dream to have a MOF with a single crystal this big, of course. We can look at it from two different points of view. So if we take the global view, we will see, let's say, the general properties of this material. We can measure its size, we can measure certain experimental properties, of course, but actually we will be losing a lot of the details on what is happening on the molecular level. And the molecular level is actually captured somehow by a different point of view, and this is the local view. So in the course of this presentation, I'll try to make it as brief as possible. I will argue that it is quite useful actually to employ complementary experimental and computational techniques that are sensitive to probing the local environment, local structural and electronic properties of the material we are interested in studying. So why is local structure important? This is just a very rough simulation of a cube that I ran. And basically, this is a 15 by 15 by 15 unit cell model crystal, where I arbitrarily colored 75% of the atoms in blue and 25% in red. And you can see that there's a certain kind of arrangement here. The arrangement here seems to be random, but certainly the arrangement isn't random here. So again, this is something that can happen in real materials. So we have the same amount of blue small cubes and relative amount of red small cubes in both model systems, but the arrangement is quite different. And this means that the local structure for these two model systems differs. And the global structure is, in both cases, different from the local structure. So on an average perspective, we will have always 75% blue and 25% red. But at the local level, of course, the structure is different. And this is what happens in complex materials. Things can get even more complicated in real materials. For example, in this third example, the first 4 planes are colored with a certain amount of yellow cubes. So at the surface, or let's say in the vicinity of the surface, let's say we can have an additional level of complexity, maybe an additional ligand that we were able to functionalize our material with just at the surface. At this point, we take our material, we stick it into a device, and things are changing because, of course, we are interested in the real-time performance of our material, and they change in different ways. So depending on the local structure, we will have a property that is different for each individual case. So how do we rationalize all of this? This is a very difficult problem. Certainly, in order to tackle this problem, it is important to note that structural properties in working conditions, so these are real-life operating conditions, they are often space and time dependent. And we would love to have local experimental probes of this complexity in real time. And of course, we're going to need a very good model to interpret the experimental results. So I will give you a brief overview of the techniques that I have used in the past, and I'm currently using here at BIDMaP to investigate these complex processes. I've actually had the most experience with dealing with complementary X-ray probes. So these are synchrotron X-ray techniques, and they may well be considered to be complementary. What do I mean by complementary? So for example, here I am displaying X-ray absorption spectroscopy. You may, of course, be very well familiar with it, or XAS. And this is a core level hard X-ray. It can be hard at least. And it is a probe of the local environment around a given photo-absorbing atom. It is essentially it can be combined with X-ray emission spectroscopy, or XES, and these techniques are sensitive up to, let's say, 5, 6, 7 angstrom, depends on how you want to interpret things. So it is a picture of the local environment around a selected element. So these techniques are element sensitive, element specific. If we're interested in going for, let's say, probing further length scales, we can actually get up to 20, 30 angstrom. We could turn to the X-ray pair distribution function, or PDF technique. I will discuss more details about these techniques in the next slides. But let me just add that the PDF for solid materials is really an incredibly powerful method. It isn't these are not, let's say, lab techniques. They're not easily implemented in the lab, even if laboratory-based instruments are available. Of course, their let's say signal-to-noise ratio isn't as good as what you would get at synchrotron. So you need to go to a synchrotron, plan the experiment, sleep one hour in 4 days. So these are not easy techniques to use. But essentially, the PDF technique, what it does, it gives you a picture of all the interatomic distances that are persistent in your material across all length scales from, let's say, 1.5 angstrom to at least 20, 30 angstrom. So this is very powerful. And what can we learn, for example, from XAS and XES? So from the X-ray absorption and X-ray emission spectroscopy. So in the case of XAS, this is just an example I'm showing here. This is a iron K edge. We are considering transitions from the 1s state for iron into the continuum, and this will be the energy required to eject the 1s electron as a photoelectron. And then at that point, there will be all sorts of scattering effects, multiple scattering effects that give rise to a modulation of the cross-section. And you see all these little bumps in, like, these features, at least a spectroscopist would call them features in the signal. And these are due to the scattering of the ejected electron with the vicinity of the atom surrounded the given photo-absorbing element. So these features are very sensitive. It boils down to this. These features are extremely sensitive to the local structural environment. We can also have, so this would be, let's say, a breakdown. Sorry, let me just add this. This would be a breakdown of a typical XAS spectrum. You have two regions, xanes. This goes from about 0 to 100 EV starting from the main absorption edge, and then the XFs region. In the xanes, we can also have these very sharp, lower intensity peaks. These are called pre-edge transitions, and they basically stem from, in the case of the K edge, from they're due to transitions of the 1s electron into bound states. So, for example, 3D orbitals, and these are very sensitive to spin and oxidation state of the given photoabsorber. Then we have the edge transition. This again is sensitive to the oxidation state. For example, if you have an iron sample with iron 4, the edge energy will be different compared to an iron sample containing iron 2 plus. If we look at XES, we kind of get a complementary, let's say, picture of the same of the same process. Here, we are looking at the decay of the excited system. Once we eject the photoelectron, we have fluorescence, X-ray fluorescence transitions, and depending on the energy of these transitions, we can call these, let's say, transitions K beta prime, K beta 1,3, K beta 2,5. These are complicated nomenclature, let's say, definitions. What can we learn from it? We can learn, for example, from this region, the shape and the intensity and the energy positions of these peaks are very sensitive to the ligands around the given photoabsorber. Of course, you need a model to interpret this, to learn this. So for example, as I mentioned before, we can get the bond distances, the coordination number, the oxidation state, spin states, ligand identity, and also obtain from XCS, especially information on the covalency of our system. These techniques are element specific, which is nice. We can probe the bulk if we use hard X-rays due to the higher penetration depth of the more energetic X-rays. We can also probe the surface. This is also quite interesting. If we use less energetic X-rays, since they penetrate less into the material, and these are often referred to soft X-rays. I will tell you a little bit more about this in the next slides. And another important part of this is that the sample environment is quite vast. So we can investigate solid samples, such as MOFs and reticular materials, gel samples, solution samples as well. And we can do this in real time, so through in situ experiments as the given process we are interested in is occurring. We can also perform multimodal experiments. So by combining a technique which is sensitive to local environments, such as XAS, with, for example, conventional X-ray diffraction, which tracks the global structure modification. So here,
What's the difference between Zanes and XFs?
yeah, sorry, great point. I didn't mention that. So Xanes is up to 100 EV.
Okay.
So the difference is the energy.
Yeah.
And XFs goes from 100 EV up to 1,000.
Yeah. Do you just need different techniques to generate the X areas of those?
No. Experimentally, you just you have the exact same setup, and you keep measuring. You just keep measuring. Let's say this is 0, so you go from 0 to 1,000 EV, and that's the XFs. So what happens if I were to extend this? You would have a curve that is like kind of going like this. Okay, and so what can you learn? What is the difference in information encoded between XFs and Xanes? So Xanes is extremely sensitive to the local geometry. So like the coordination number, if you have a 5 coordinate compared to a 6 coordinate, it will be very different. Also, 6 coordinate octahedral, perfect octahedral compared to a 6 coordinate where the octahedral geometry for some reason is distorted. These peaks will be very different. The XFs, on the other hand, you will not really be able to identify with high precision the bond distances. So there will be an error on that. The XFs, on the other hand, is very sensitive to the bond distance. So you can have like, let's say, an XFs analysis that identifies, I think, with 1 angstrom, 0.01 angstrom of error, the bond distances.
Yeah. Like when you do a measurement, are you doing always both Zanes and XFs, or?
It depends on the beamline. There are actually some beamlines. For example, there are beamlines where you can do Xanes and emission together, and these beamlines don't allow XFs, actually. But let's say if you're not interested in the X-ray emission beamlines, most beamlines will just allow you to do the full XAS spectrum.
It's the same fundamental physics, though, right? It's just called 2 different things. Okay.
Yes, exactly. Yeah. This is like the extended X-ray.
Okay, sure.
Yeah, that's why there's an E. Yes. Okay. So this is a first case study I wanted to briefly tell you about, where we employed these techniques to obtain some chemical knowledge. Actually, this is not related directly to water harvesting, but I think it's, let's say, interesting to get familiar with one of the systems that I will later discuss about for water harvesting. So this is the MIL 100 iron MOF. you might know this MOF. This is one of the prototypical MOF systems that have been, let's say, explored in the literature. It is a giant MOF, so the unit cell is really, really big. And it is, let's say, comprised of this sort of oxo building unit where you have 3 iron sites. In the pristine MOF, these iron, these iron sites are in the 3+ oxidation state. They are all octahedrally coordinated, and 2 water molecules cap the octahedral position for 2 of the iron sites, and the 3rd iron site here is coordinated either by a hydroxyl or a fluoride, depending on the synthesis. So we were interested here in understanding the mechanisms, the molecular factors influencing the ability of this MOF to actually catalyze the reaction between methane and oxygen to form methanol. This is, of course, a very, very relevant reaction for the chemical industry. There had been previous work by the Gagliardi group and collaborators investigating this system and for this reaction in the presence of N2O, so a different oxidant, more expensive, less abundant, and we were curious to see whether oxygen could also, let's say, whether this reaction could also occur in the presence of oxygen. So we performed all these synchrotron complementary measurements at the European Synchrotron facility in France. And here I am displaying basically the X-ray diffraction patterns of the pristine MOF, thermally activated at around 200 degrees for a certain amount of time to remove the physisorb molecules, and the XRD pattern of the MOF after the reaction. So do we see any differences? Not really. So nothing's changing apparently on the global structure. We can understand very well by looking at the presence of peaks, the persistence of peaks in the XRD, that the MOF isn't destroyed. At least we know this. Well, what is happening at the local level? Wow, many changes. So let me disentangle this. So here I am displaying the iron K-edge XAS spectra as a function of time and temperature. So we go from the blue curve, which is the spectrum of the pristine MOF, the resting state, while we are heating. And this is and the curves are becoming redder and redder. And you can see that the edge energy shifts towards the left, and this is because the energy required to extract the photoelectron is less, and this is because there is a reduction, progressive reduction as a function of thermal increase. And you may see that 2 peaks present in the pre-edge in the spectrum of the pristine MOF actually progressively coalesce into a single peak. This means that there is a consistent structural change around involving the iron local environment.
Is this under argon or oxygen atmosphere?
This is helium.
Helium atmosphere.
Yeah, this is very important to note. This is all under inert atmosphere. Helium, yes. So actually, we ran some simulations, calculations on this, and what we understood is that the pristine MOF, as I mentioned earlier, has 2 water molecules coordinating these 2 iron sites in an octahedral geometry, and there's a hydroxyl capping the 3rd iron site in the trimer. Once we reach 200 degrees, we've basically removed most of the 2 water molecules in the trimeric unit. So 2 of the 3 iron sites are 5 coordinate. And this is this leads to the increase of this peak. So these 2 transitions are related to octahedral iron. And then the single peak is related to the presence of 5 coordinate iron. And then once we go up to 250 degrees, actually we are removing the hydroxyl and reducing the 3rd iron site to iron 2. And this leads to the very, let's say, significant shift of the edge energy towards lower energies. And also the valence to core XES, so this is basically the iron K beta 2,5, sensitive to the covalency of the system. It is also sensitive to these structural changes. So if we consider for example, the XES spectrum in blue of the pristine MOF, this is quite different compared to the XES spectrum of the thermally activated MOF. So we have actually demonstrated with just by following the thermal activation that these techniques are sensitive to change in local environment.
Do you have any idea where the other hydrogen comes from?
That is the hardest question.
Well, I was the lowest when we studied.
Yeah,
those,
we actually, nobody knows.
and nobody knows. where
Nobody
that-
knows.
Oh
We wrote in the paper, nobody knows.
Yeah,
It's actually literally.
Mysterious, this mysterious hydrogen.
Yes,
Out of nowhere.
I think Jeff Long doesn't know. Nobody
So
knows.
weird.
Yeah, I know. Nobody wants to know yet, but but that's actually a good point. Identifying the key reaction species. This was the aim. So okay, so these are the experimental data so now we have the activated MOF. This is shown. The corresponding spectrum is shown in red. And then we run the reaction in the presence of oxygen and methane at 200 degrees. And you see that there is a shift towards higher energies of the main adsorption edge. This means iron 2 is going to iron 3. And at the same time, this very, very small shoulder decreases. This is actually due to the reduction of the oxidation of iron 2 to iron 3. And we constructed, so this is all initiated, of course, by oxygen binding to the iron 2 sites. Progressively, we constructed a hypothesis for the mechanism. There is a very small amount of methanol that is produced, very, very small. We track this with real-time mass spectrometry. And at the end of the day, the XCS data collected on the post-reaction catalyst, which is shown in green, allowed us to hypothesize that the deactivation actually occurs when the catalyst deactivation occurs, because it does occur, it leads to this species here. So let's say it leads to the presence of trimeric units which are hydroxylated. And this seems to hint to the hypothesis that the pore aperture size, which is the big size of the pores in MOF in MIL 100, actually critically affects deactivation. Okay, so let's consider the same MOF, always MIL 100, and we actually we're interested in investigating the mechanism of the water harvesting ability of the same MOF, because this is also a water harvesting MOF. So if we again look at the structural properties of the MOF at increasing length scales, we start from the trimeric unit. We know all about that now. Then we have two different pore windows. So there's a pore A with a 29 angstrom diameter and a pore B with a 25 angstrom approximately diameter. And the unit cell is really large, as I mentioned, 73 angstrom of cell parameter, and these are about 13,000 atoms. Can we obtain, so we were interested in answering this question, can we obtain short and long range information on the behavior of water absorbed within the MOF, both from an experimental and computational perspective? So to answer this question, we actually made another trip to the European Synchrotron, and we performed a combined XAS, X-ray diffraction, and PDF experiment. Just to briefly show you what a PDF experiment looks like. So you have your sample, which is somewhere here. This long thing is the beam hitting your sample. And then in the case of PDF, you collect the diffraction on this large and very expensive 2D detector, which generates a 2D diffraction image, which is then converted to 1D. You apply different, let's say, post-processing normalizations and transformations, and then which are then followed by a Fourier transform, and at the end you obtain the PDF. So this is what a PDF would look like, and all these peaks are, as I mentioned earlier, related to the persistence of a specific distance, interatomic distance present in your material. So for example, you have the carbon-carbon peak, the iron-iron first neighbor peak, and so on. So, okay, so let's look at the thermal activation of MOF. Let me take a step back. So what we did is we first thermally activated the MOF. We then brought it back down to room temperature and we exposed it to water vapor. And then we follow the thermal dehydration of the fully hydrated MOF. So this is what we are following here. These are the powder X-ray diffraction patterns going from the hydrated MOF, and the corresponding pattern is shown in blue, to the thermally dehydrated MOF in red. And you can see there's a small shift of the peaks towards higher 2 theta degrees, and this is indicative of a slight unit cell contraction. If we look at the PDF data tracking the thermal dehydration, we actually see that there's a double peak. One of the two peaks are, let's say, located at 3.35 angstrom. These merge into a single peak at 3.23 angstrom, and this is due to a slight decrease in the iron-to-iron distance as water is removed from the MOF pores. And again, of course, the XAS shows very, very significant differences. These are quite similar to what we had measured in the previous work. So as we remove water, so we're going from the blue, the water, let's say, saturated MOF, to the red, the water dehydrated MOF, there is a shift of the edge energy towards lower energies and the increase of a single peak in the pre-edge at the expense of this double peak. And this is due to the fact that we are removing the water molecules. So water, the iron sites aren't octahedral anymore, but they're progressively moving towards a square pyramidal configuration. At this point, we perform some molecular dynamics simulations of the confined water with the aim of interpreting the results. So here I am showing representative density maps of the oxygen of the water molecules of the MOF saturated with increasing amounts of water. And you may see, so basically when it's all red, there's water everywhere. You may see that actually the redder regions start appearing in specific regions of the MOF unit cell in this representation. And this basically was attributed, we attributed this to the filling of the pores B, which fill before the pores A. So here, these are all pores B. And then the A pores fill at higher water loadings until MOF is fully saturated. We actually, let me add that we did the same simulations up to 40 water molecules per trimer. I don't have the image here, but this is not the highest loading we explored. And what is happening to the local structure from a theoretical perspective? So this is a simulation of the experimental iron K-edge xanes. So this is the first 100 EV, more or less, region on the left. And then you have a comparison of a theoretical curve calculated from a model where all trimeric units are bear the iron sites in a square pyramidal configuration. And you can see that there's a single transition in the pre-edge region. At this point, we computationally add one water molecule per iron site, actually 2 water molecules per trimer. And you can see that the theoretical calculation shows the presence of 2 peaks because we are going from a square pyramidal to an octahedral configuration. And then we keep increasing, always computationally, we increase the water loading in the MOF. We calculate the corresponding xanes. And you can see that the intensity of these 2 peaks in the pre-edge region starts to change. And this is actually, we were able to attribute this actually to the existence of hydrogen bonding between the water molecule directly coordinated to the metal sites and the, let's say, second sphere water molecules. This progressively leads to a network, and at the end, at the higher water molecule loading, we recover the experimental, let's say, pre-edge intensity ratio quite well. This for XAS, by the way, is considered excellent agreement since we are not doing fitting. Let's say this was a very exciting result for us. So if we look at the changes in hydrogen bond topology as a function of water loading, we can actually correlate them to the spectral XAS fingerprints. So this was a very, let's say, rough analysis of the hydrogen bond topology based on the MD simulations. So when you have a number of water molecules per trimeric unit equal to 3, basically we defined different possible donor-acceptor arrangements for the water molecules. So you have, for example, a certain amount of water molecules that do not donate and do not accept 0D and 0A hydrogen bond, which is defined as I'm showing here. Some water molecules donate one hydrogen bond and do not accept any, and some water molecules donate one hydrogen bond and accept one. And you have, sorry, let me go back. And you have a double, you do have a double peaked pre-edge in the theoretical XAS region, but the intensity is different compared to the experiment, the relative intensity of these two transitions. As we increase progressively the amount of water molecules in the MOF, the distribution of donor-acceptor pairs changes, and so does the theoretical XAS spectrum. And we progressively move to a situation where we are recovering, as I showed earlier, the experimental relative intensities of the pre-edge, of the two pre-edge peaks. And at the higher water molecule loading, we have, let's say, the predominance of waters that donate two hydrogen bonds and accept two hydrogen bonds. So the result of this analysis was that the topological properties of water are somewhat encoded in the XAS signal, even if this is a very local snapshot around the iron sites. It is sensitive to second shell structural modifications.
Yeah, so
Yeah.
I'm a little confused. So the experiment shows one peak, but there should be two peaks, right? Or
Yeah, sorry, the experiment shows two.
the experiment does show two.
Yeah, I have here I'm showing only one. I don't know if you can see the two here.
Okay. Oh,
These
that's what
are actually
hydrated
two.
versus-
Yeah, I know it's a little harder to see.
Gotcha. Okay.
The intensity isn't perfect, like the relative intensity matching isn't perfect, but
Yeah.
yeah.
And then for doing the theory on this, are you guys just doing ab initio?
No, this was actually done on an available force field that was published in the literature. I don't know if I have the. No, I can share more about
Yeah, I'm just like the force field won't give you excitation. I'll ask you about it later.
Yeah, sure. Yeah. So basically, yeah, we can talk about that later. Yes, so this was basically the main conclusion of this work. And as a last case study, I just briefly I still have some time. I just wanted to briefly tell you about how these techniques can be used to investigate the surface effects. So as I mentioned earlier, if we change the energy of the XAS probe and we turn to soft X-rays, so here I'm talking about energies that go from 0.2 to 1.6 keV approximately, we are actually intrinsically diminishing the penetration depth of the X-ray probe due to the let's say lower energies. And the way that these beamlines the way the soft X-ray beamlines are built, the detection techniques are at an increasingly surface sensitive layer. What do I mean? So for example, there's a detection mode called total electron yield, TEY. Basically, this is based on the fact that the incoming photons go through X-ray transparent membrane. They hit the sample at a certain point. The sample emits electrons, such as similar to almost XPS process. And then you have the progressive, let's say, release of electrons, and these electrons are measured as a drain current. This process, of course, is intrinsically surface sensitive. So soft XAS measured in TEY mode will be sensitive to about 5 to 10 layers below the immediate surface. So we actually applied this technique to investigate the properties of magnesium MOF 74. So this is another prototypical MOF in the MOF literature. It is constructed with these hexagonal channels. They're approximately 11 angstrom wide. And the magnesium sites actually coordinate directly water molecules. If you remove the water molecules, this is an octahedral geometry. If you remove the water molecules, of course, the octahedral geometry will be broken. So what happens we can have a very quick overview of the arrangement of water inside the MOF from classical molecular dynamics simulations. These are simulations performed from always using a force field that was developed by previous groups. So if we consider a loading of one water molecule per metal site, actually these water molecules, and there has been a lot of work on this, are tightly bound to the metals. And if you remove them, you basically destroy the framework. So they're almost bulk-like. If you increase the water molecule loading up to a maximum amount of 5 water molecules per metal site, of course, we have, let's say, the pore fully, let's say, populated by water. So we can, again, track the progressive population of the local structural environment of a selected magnesium site by water. For example, at a loading of 1, 2, 3, 4, and 5 water molecules per metal site, and then calculate the corresponding soft XAS magnesium K edge. So this is the magnesium K edge, I forgot to mention that before, which is located about 1,300 eV. So we calculated the soft XAS curves based on the molecular dynamics snapshots. And you may see that there is quite a change. I mean, going from the XAS spectrum shown here in red, calculated for the lowest hydration level, there is like a bump. Again, these are like spectroscopy terms, so sorry for this. But going from the lowest hydration level to the full hydration level, there is an increase of this feature here, which becomes much more intense. And this for XAS people is considered to be a very, let's say, significant change. So this is a surprise because magnesium is not changing its coordination geometry. It's always octahedral, but still we have significant variation of the local structural properties without a change in coordination environment.
These are the virtual states.
Sorry?
Is the edge features as exciting to unbound states, right?
I think so, yeah. I think so. And at this point, it's time to compare the experiment with the theory. So actually, the experimental data is quite similar to the theoretical data. So here I'm plotting the experimental magnesium K edge of the hydrated MOF, shown in blue, compared to the experimental K edge spectrum of the dehydrated, partially at least dehydrated MOF, shown in red. And you can immediately see that the edge position, again, similarly to the other MOF, so there must be something, let's say, common between these systems with these water experiments. The edge energy is shifted toward lower energies, and there's the increase of a pre-edge peak. And there's also this, let's say, bump here, which is present in the spectrum of the hydrated MOF, but not present, or at least less intense in the one of the dehydrated MOF. And the theoretical curves, at least qualitatively, reproduce this trend quite well. And the important thing to note is that this pre-edge peak is actually due to the inclusion in the model of 5-coordinate magnesium sites. So a part of the magnesium sites loses the water molecules directly coordinated them during the thermal dehydration properties. And we actually estimated the amount of open magnesium sites to correspond to about 20% of the total number of magnesium sites in the MOF. So we also calculated water probability density maps at increasing water loading. So you may see, again, we're highlighting in red the regions where the oxygen of water molecules are, where the water molecules are most are present with higher probability. And as you increase the water loadings, you can observe that here, for example, and here there is an increasingly higher probability of finding water molecules. So if we change this representation and look along the channel of the MOF74 system, we can actually identify intra-chain water bridges. So you have different chains of magnesium sites, and these are like bridging chains. And water will first coordinate the open magnesium sites, and then there will be bridges created between one chain and another. And then you have interchain water bridges. So this is along the same chain, and this is along two, let's say, chains that are close to each other. And let's say to conclude this work, we also ran some calculations to study the dynamical behavior of confined water as a function of water loading. So here I am basically considering just the systems with the lowest and the highest water loading. So n equals 1 and n equals 5, basically. And you may see in this panel, in panel C, a plot of the reorientational correlation function for water. So this is basically a function that calculates the ability, captures, let's say, the ability of water to reorient. The faster it decays, the faster it reorients. The slower it decays, the slower water molecules reorient on average. And we find consistently with previous results that as the water amount in the MOF increases, the ability of water to reorient increases. This is due to the increase in hydrogen bonding, which slows down the reorientational ability. And also, of course, the translational properties of water are affected. If we consider cylinder, if we carve sections with a cylinder shape at increasing radii, centered on this in the middle of the MOF at the highest water loading, and we calculate the probability of finding water molecules within these, let's say, increasing shells, or at least these increasing volumes, we find that the probability of finding water in the middle of the cylinder is quite low. It decreases at least quite fast. This means that water is moving away quickly from the middle, and of course, it moves away less quickly if we increase the radius. So basically, the translational mobility of water increases clearly as a function of distance from the channel walls. So with this, I wanted to conclude. I acknowledge, of course, all my previous collaborators. I'm sorry I don't have the slide here, but this work was largely, actually was mostly done in Italy. And of course, the Yagi group here in Berkeley and the BIDMaP for their amazing support. So thank you.
Any questions?
On the previous slide, I missed what's, so you're studying the dynamics as a function of time, like what's the impulse, like what's the change? What is this in response to?
Oh, this is just as a function of the simulation. As a function of simulation. So during the simulation, if you're referring to this, yeah. So during the simulation, how much time does it take on average the water molecules to reorient?
I see.
If you had a study a similar disordered material that wasn't crystalline,
This is what I'm studying actually.
like, is there anything like translational from these like computational techniques that you can take away?
I would say so this is a great question because this is exactly what I'm doing. I haven't showed, unfortunately, the results are still preliminary on what I've been working on here in Berkeley with Professor Yagi's group. I'm actually studying disordered materials. Yes. So your question, if I understand correctly, is can you translate this methodology to that or no? Do I understand?
Yeah, I mean,
Yeah. This is exactly what we're doing. Yeah.
okay.
Yeah. I mean, of course, it's harder. You need what we're learning is that you need more technique, even more complementary techniques to make sure that you're not making things up, let's say. Because if you only have PDF, for example, maybe you have a good picture of the bond of the distance of the interatomic distance variations, but you have no idea of the ligands that are coordinated to the for example, if you have a metal, to the metal sites. You can have a hydroxyl, a water, an acetate for the PDF. If it's just a fraction of the sites that change their local environment, it will be the same. You won't have the sensitivity to see that, yeah.
And then in the first MOF, you also did like a similar probability map that was like projected down.
Yeah.
And the unit cell, like it was blue on the outside. And I'm wondering why that is. But yeah, like it's blue on the outside, but looking in the like probability intensity, it seems to me that you should see red up to the.
I think this is a great point. I think this is just because of the code I was using to do this plot.
Okay,
For some reason, I must have added, or it must have been a default of the code. Like it's just a visualization thing. So I just added a blue thing to the Z. Like I hope.
but you guys did like periodic boundary conditions.
Yeah. Of course. Yes. Yeah.
Difference between the top and the bottom?
Oh yeah, this is just let's say here the water molecules are shown as molecules. It's just a visualization difference. And they're shown in blue for some reason. It is not the best way of displaying this. Sorry for that. So the water molecules here are shown in blue, the oxygens. And here you have the probability of finding the oxygen of water displayed in red. But it's exactly the same.
Nice.
And of course, PBC are enforced. Yeah.
Francesco, I have a question. Can you, like, for the next slide, can you expand a bit more, or you get the